Hello, we are Chris and David Brownrigg. Chris is an artist and I am primarily a computer scientist. We've been working together at times on computer art image processing for over 35 years. I shall be making the presentation as the emphasis is on the computing side, though all the content is driven by and rooted in the application to visual practice. Most of this presentation is examples of creative changes to images, image sequences and movie clips, so that they look very different from the original. Firstly, though, for context, we describe some of the methods that we have devised to make the changes. While there is much theory and mathematical content underlying the methods, it can be briefly and effectively covered in a pictorial way that makes it generally accessible. The examples follow a progression from sources of materials through their form for use to the structures that mark human presence in locations. In parallel to this, we progress from simple views represented by single images through multiple views of one location to views of a location over time, illustrated by animations and movies. Since we began our periodic collaboration in the early 1980s, our general approach to computer art has been to abstract from images of reality in such a way that the intermediate stages usually cannot be envisaged directly, and, however abstract the outcome, it is determinably and often recognisably related to the original. In some ways, this reflects an idea of what some artists, poets and musicians have tried to achieve with hallucinatory drugs for many centuries. In our recent work, a major element has been to take multiple global transforms of images to form sets of modes, values uniquely describing the original image and from which it can be reconstructed. We then mix, manipulate and select modes from which a new image is constructed. A familiar example may help to clarify what we do. JPEG compression of images involves a sequence of processes, ending with recording a codified representation of some modes. The modes are the result of taking a cosine transform of each 8x8 subimage. Each subimage is represented by 64 amplitude values, the products of cosine transformations for each row and each column. The picture shows the shape of each of these 64 functions over a subimage. For example, the top left constant value is for cosine 0x, cosine 0y, and is a measure of the average pixel value over the subimage. JPEG compression then approximates and selects from these mode amplitudes or sizes in such a way that the resulting image looks, to a human viewer, like the original, while the mode data takes less storage space than the original raw image. Here we're interested in looking at all the modes from 5 transformations, which are cosine, waves as used for JPEG, Fourier, a mixture of cosine and sine waves, Walsh, square waves, slant, sawtooth waves, hair, impulse waves of varying widths and positions. We apply the transformations independently in each direction. This gives 25 sets of mode values in each part of a 2D image and 125 sets for 3D data, such as a stack of images as in a movie clip. It is the mode values from all these sets that we manipulate and from which we select. We relate mode values from different transforms by the number of times the function crosses the x-axis. Transforms can be applied to a whole image or separately to a set of subimages. For subimages, they can form a connected set of rectangles covering the whole image, as JPEG, or a randomly sized and oriented, possibly overlapping set, or a set of user-defined quadrilaterals mapped to rectangles for transform processing. We use 2 approaches to processing. One is to process the whole image or image stack, treating the modes from one transform as belonging to another transform in making a new image. Another is the B transform, From the set of all transform modes, we use our own algorithm to select some of the modes and treat each as belonging to the transform that produced it. Now for some examples. Building materials come from the landscape, with or without existing buildings. This dolerite is near a very old structure, Hadrian's Wall. Dolerite is hard and is used as concrete aggregate or a facing stone. The Romans seem to have found it inconveniently difficult to use for Hadrian's Wall and chose other more workable local stone and some softer materials. The centre and right-hand images were made from the original using the B transform. The algorithm for mode selection exaggerates and modifies colour near a reference brightness level, while driving darker and brighter regions to more extreme values, thus also emphasising pattern. Each of the two images uses a different reference brightness, and each gives a very different view of the scene. Sometimes an apparently dull image with little brightness variation can work well, as the colour exaggeration applies across the whole image. In this case, the starting point is a partially shaped stone on the shady side of an old church in Kent. In this original image, some soft colours come from the stone and some from old lichens. With such a low contrast image, the B transform gives very rich colours and pattern emphasis, a result perhaps unimaginably different to the original. Moving to a larger scale, this is London in 2006, with some of the crowd gathered to watch a performance of The Sultan's Elephant, a story of connections. The scene is one moment at one place of an event spread over several days and many locations across the city. We looked at the image in two ways of the many that are possible. One was to process the whole image in a single way. The other was to divide the image into irregular quadrilaterals that had some relation to zones in the image. Even for these two views, there are many alternative treatments, and we illustrate just a few of them, following a line of increasing abstraction from the original image. This is an example of treating the image as a single entity. The Walsh square wave transformation is taken, representing the image by a set of corresponding mode amplitudes. Each mode is then interpreted as belonging to the slant sawtooth wave transform, and the slant waves combine to form a new image. There is some abstraction, but much of the scene is still recognisable, though within it parts of the image are redistributed across the space. In general, every part of the new image carries some element of every other. In these two images, the B transform was used. The original was mapped to 1024 by 1024 pixels for the left-hand image, while for the right each user-defined quadrilateral was mapped to 1024 by 1024 pixels. In each case, the mapped squares were broken into 256 64 by 64 squares. For each, the B transform was taken, and 128 of the 102,400 modes were selected. The squares were then mapped back to their original quadrilaterals. The left-hand image retains a recognisable appearance, while the right-hand image is a little more abstract, with the twisting effect of mapping in and out of the processing squares causing some distortion in parts of the image. Here, there is a greater level of abstraction from a more complex use of the user-defined quadrilaterals. The B transform was applied twice to give two intermediate images, one selecting 128 modes per 64 by 64 subimage, in the other selecting only 4 modes. The two intermediate images were differenced, pixel by pixel, and the result colour inverted. That is, for each value of each colour component, in the range 0 to 255, a value of 255 minus the existing value was taken. What results is more abstract than before, with the buildings, the elephant and the people now merged into a whole that can only be separated by reference to the original image. As a last example with this scene, we can see that retaining even fewer modes gives even more abstraction. This is not unexpected as we are throwing away more information about the original. Again, two B transforms are taken, selecting 16 modes per subimage for one and 4 modes for the other. The top left image shows a difference, and at the bottom right is the inverted difference. Now the original scene is abstracted to simple patterns that are varied and bright, with some sub-areas having the character and pattern of flags, from which we might reflect on the multinational character of the event. This is a scene in another city a few years earlier, though what is shown is centuries old. Brunelleschi's dome on Florence Cathedral is so well known that we may forget the level of achievement in its design and construction. We took all possible combinations of transforms, interpreting the modes as belonging to another transform, with rows and columns treated the same way in each instance. In the block of 4 images, a few examples are shown. Top right being cosine modes interpreted as slant, bottom left is Fourier as Walsh, and bottom right is Walsh interpreted as Fourier. In one change for this processing, a version of the sine transform was used in place of the Hare transform. We then animated a transition from image to image, starting with Fourier modes interpreted as Fourier, and finishing with cosine modes interpreted as cosine. Naturally, in such cases, the resulting image is the original, which means that the original appears at the start and end of the animation and at a few points in between. The animation shows the flow between transforms, from reality to abstraction and back, with a softer effect from interpreting modes as Fourier, cosine or sine, and a harsher effect from interpretation of modes as from Walsh or slant. For another country and culture, we looked at the Rionji formal dry garden. The two photographs give some idea of this UNESCO World Heritage Site, with its aesthetic using a limited number of shapes significantly positioned. We made a video clip by panning across the garden from a single position near the viewpoint of the lower right photograph. This gave a varying view over a short time with constant light conditions. What is relevant to our processing is that in any one part of the frame, different parts of the garden appeared at different times. The video clip was sampled at low spatial and time resolution to keep the size of the dataset manageable for the relatively low-powered computer used for processing. The data, a stack of 2D images, constitutes a 3D set of voxels to which we can apply three-dimensional transforms. There are a very large number of possibilities, many of which can give a confusedly abstract result, so we chose a very simple process. This was to take a Fourier transform in the time domain only and interpret the modes as being from the Walsh transform. The result is a limited colour palette with softened shapes. The mode interpretation means that, at any one time, elements of earlier and later images appear in fluctuating ways, essentially ghosts both of the past and of the future. Lastly, we turned to a domestic scale of architecture and showed changes over time. This is a house in the Kent countryside. It was built in 1900 and had been subject to some changes over time, a few of which were not of high quality. The photograph at the top right shows the result of removing some old changes and slightly extending the house over a period of about 4 months. The bottom right image shows the result of the building works being cleared away and replaced with a structured garden which has since matured. During the change process, a daily photograph was taken from about the same position and time of day, with similar tilt and direction for the camera. Forming the image sequence into an animation, the tilt direction variations are very noticeable, masking what are much greater daily changes due to varying weather and season. The distraction of that misalignment can be seen in this animation. As this misalignment is visually intrusive and distracting, the next step was to improve the alignment of the image sequence. Given the time span of about 4 months, there were significant variations in day length and angle of the sun, as well as changes from day-to-day variations in weather, wet and dry, cloudy and sunny. Again, there are many possibilities for processing the image sequence, and several were tried, with effects ranging from subtle to garish. In this example, we took a Fourier transform on the rows and column of each day image and a Walsh transform in time. We then interpreted the daily Fourier modes with a Walsh transform and the Walsh time modes with a Fourier transform. This mixes each element of each image partly to all other places of all other images. All times and places are a little connected. This abstraction is still recognizable if the original is known. To help connect abstraction and reality, we floated some varying polygons across the animation, filling each with a corresponding image for that part on that day. The result is a fluctuating abstract scene in relatively subdued colours with a reminder of the original building transformation within it. In summary, what we have shown is how our approach to image transformation via a non-visual space can give a new way of looking at familiar objects and scenes, including everyday and exceptional environments. There are many possibilities, including creating images that can aid creativity in other media, such as painting. Our approach can be developed to make a complete presentational display. That is, for a given location, structure or event, a range of techniques can be used to give a wide variety of connected revisualizations. Alternatively, one of the revisualization approaches can be applied to a range of structures or events of the same form, such as leading religious or cultural centres in several cities, linking them and their cultural icons in a novel way through the language of our representational abstraction.